let's begin the lecture for today. We want to understand efficiency estimation. We are going to use three approaches quickly to do the estimation, and then we can go ahead to understand. So the first thing is, I want you to consider the following here as input resources. And then the following here, which is the sales, as output resources. That is how I wanted to look at this. And I wanted to probably document that because I want us to look at this from the operations research perspective, from linear programming perspective. So you have some resources, but instead of having these resources for just one company or one decision-making unit, like DMU1, you are having it for multiple companies because we did say that the target variable, the objective function value is the efficiency score. The objective function value, which is in this case, is not the profit. It's not profit. It is rather it's not profit, but it's rather and it's not loss, and it's not cost, it's not distance, it's not time, but it's rather efficiency scores. And because it's efficiency scores, that efficiency score of a particular decision-making unit has to be maximized. It has to be maximized. In this case, you are considering the efficiency score as more of it is better. And the efficiency scores is between 0 and 1. You will see the model, the linear programming model will constrain it to be between 0 and 1. Now, the idea here is that you have multiple decision-making units instead of one, and each one's profit, but this time not profit, it is efficiency. Each one's efficiency has to be maximized. And normally in the linear programming, you have the story in such a way that you know the coefficient of the profit or the coefficient of the costs or the distances. At this time, you don't know the coefficient of the efficiency scores, but there is the coefficient of the efficiency scores that will show later time. The goal is to be able to find the target score that each one has to have. It's just like the objective function value that a particular company has to have. If it is profit, then the more is better. But of course, you can't go to infinity profit. It's not possible. And here too, you can't go to beyond an efficiency score of 100%, and you will understand very soon why. So you have these resources, input constraints or input resources, and then output constraint or output resources. Now, the first thing you want to do graphically is to scatter plot this. So let's scatter plot it. Oh, by the way, I'm giving you the data set in your group page. So you can open the Excel and you can fill the data set. Now, let me see if I can open that same data set and show you something. Okay, let me see if I can open this data set here, and then I can show you something there. Can you confirm if you can see the data?
Send, please.
You see?
Yes, please.
Yes.
Okay. So you have this data set that is here, staff, which is the input constraint or input resources, and then you have that of the sales, which is output constraint. Now let's try to generate. The first thing we can do is to use a simple ratio, because that's what financial analysts do. Simple ratio. They calculate a lot of ratios: return on assets, return on equity, earnings per share, capital adequacy ratio, and all of those. Now, a simple ratio could be, and remember, in this case, because the output resources are sales, you want to have more of it. And because input resources are staff, you want to have less of it. That is to determine efficiency. The less of the input resources, the more efficient you are. And the more of the output resources, the more efficient you are. So one best ratio is to do it as the output over the input, okay? Y over X. That's a very simple ratio that one can actually adopt. So for each decision-making unit, you can find its Y over X. And so for the first one, 1 over 1 is going to give you 1. 3 over 2 will give you 1.5. And then on and on. 6 over 7 will give you 0.86. So on the basis of this, if you want to know the company that is the most efficient, which company would that be? Which decision-making would that be? Obed. Which decision-making will be set to be the one that is the most efficient? Chris.
That'll be 2.
Okay, did you call Obed?
Yes, please. He joined, but I couldn't hear you, so he's rejoining.
Obed, can you hear us now?
Yes, now I can hear you.
Well, I would suggest that you don't mute yourself so that you encounter problems again. Just keep it on. Can you do that?
Yes, I've kept it on.
All right. So the best company in this context is DMU2. Why did you say that, Chris?
Because the ratio is more than 1. That means that given one staff, they produce sales about 1.5.
Okay. But it's not necessarily because it's more than 1, but it's because what? What if DMU2 has a value of 1? Which company would you say is the most efficient?
Then there will be a tie, about 3 of them.
Exactly. So not because it's more than 1, but because it's the one that has the highest value, the highest ratio. Okay. So in this case, those that have the highest ratio, if they are all having the same highest ratio, they will be the most efficient. That is the simple way to determine efficiency. But there is a problem with the simple way. It has advantages, of course, because it's simple to produce, to compute, easy to understand, So it's very, very cool. It can even allow you to look at a specific aspect of the firm. For example, you can look at return on asset, which can help you to measure just the asset value of the firm. You can look at return on equity. It can help you to know the return you gain from equity utilization. So you are able to see the benefit on that. You can look at return on labor. You can look at different aspects of a company's performance. However, the problem is that you cannot incorporate multiple inputs and multiple outputs. Okay, so if you look at this, the ratio can only be obtained when you have one aspect which is staff and one aspect which is sales. Okay, the moment you begin to have staff, capital, this, that, all put together, and you want one single ratio with all of them put together, it's not possible. So ratio is great, but it cannot handle multiple inputs and multiple output according to several others. So how do you consolidate multiple inputs and multiple output? That is what ratio lacks. Another disadvantage of ratio is that it uses partial measures of performance. We've said that already. The performance is not holistic, it's partial. It's not total, it's partial. Also, it doesn't assume the possibility that, things that are in real life are not straight line. Life is complex. Life is not a straight line. The statement life is not a straight line means that the returns to scale are not constant. You see, a constant return to scale is where you have the relationship between input X and output Y, and then you have a constant return to scale from the origin. So from the origin, you have a straight line. How is it that when I write it? You have a straight line from the origin, which means that if you should increase the input by 20%, you are going to increase the output by 20%. Obed, is that real in real life?
Look, it happens.
Yeah. And what I mean is that always the case in real life?
No, it's not the case.
What is the other case?
Please, I don't get I don't get your question.
I asked you whether that is the case in real life. And he said, no, that is not the case in real life.
Yes, the other case is in real life you can put in something, then you get less of it.
Or
More, so you can also put in something which is less, but you get more of it.
yeah. So in real life, things are not constant all the time. It can be constant, it can be non-constant. That non-constant is what we call variable returns. And this variable returns makes ratio breaks down because ratio simply assumes constant returns. To maintain the ratio, okay, there must be constant returns assumption. The next disbenefit of ratio is that it doesn't tell you the benchmark. It doesn't tell you who are the role models. Now, for example, if you should go back here and look at this, even though DMU2 is getting 1.5, it is not necessarily a role model to the others. How do we know that? Because it may have certain size that is not the same size as the other companies. They are not of similar sizes. They are not. For example, this company may be so big, another one may be so small, and yet you are assuming that they are of the same sizes when that is not really the case. So that breaks down this whole idea of constancy. So you can't compare. You can't compare a university student with a primary school student and say that this guy is smarter than this. No, you can't. Or this guy is more efficient than that. No, you can't, because they do not study the same. Even people in the same university might be studying different subjects and therefore may not necessarily be comparable. Ratio doesn't capture these. And finally, ratio, it doesn't allow you to decompose the performance, the ratio performance, into many sources. So you don't really know what is driving the performance. When you go to the previous one, you check the value of 1.5, you don't know what is causing the 1.5 to be 1.5. Is it because the inputs are smaller or because the output is bigger? You can't really tell which one. And therefore, we need another alternative to handling this. Well, in the world of statistics and econometrics, the easiest alternative one can think about, came along the line. Okay, and that is regression. Regression analysis is simply a measure of the mean. So we decide to scatter plot the data. Now, how do you scatter plot the data? Take your data set. You can follow it up with me as I scatter plot this data. One thing you can do to scatter plot the data is you can highlight the inputs and the output. Go to Insert. Okay, now this thing is frozen. Okay, good. Go to Insert, and then under Chart, click on this section here and choose the first one, which is Scatter. In fact, you can use Bubble. I was even going to use Bubble to show, but it's the same thing. So this is Scatter. When you hover, at the top, you see Sales. Sales is not a title, so you can just click on Sales and choose your Delete key to delete it. You can change the coloring, okay, whichever way you want. You can increase the size of this. So you can click here and change the colors. Whichever way you want the colors to change, you can change that. Okay. And then you can also increase the size if you want. So if you click on this little one here, at the top, you see Format. Then you can look at Chart Elements or Styles. Okay. And you can do a lot of things with it. Let me just go here. So here, oops. And then you can me click it again. You can choose data labels, okay, to be able to have the names of the data on it, and then later on change it. But for now, we can just choose data labels. Okay. You can center the data, put it above. I am trying to put it all above. Okay. And you can also show it as a call out, whichever way you want. You can have multiple options and then just have those multiple options. Now, under the multiple options here, you can just click on this separator. In fact, you can even go to markers. Where is the markers? So close this one. Oh, come on.
The marker is the first.
The first one. Okay,
The first one. No, the first.
All right. Click on solid line. Actually, is a line I'm showing. I should show this plot itself. Good. And then now I can have the markets here. So you can click on this and select this marker. You can change it. This is using the red type. So if you have the built-in here, you can change it and choose any one that you want to choose. Okay. Let's say these stars. And then you can increase the size of the marker here. Now it's getting too big. But let me just use this one as a way. So there are so many things you can do. But more importantly, after you've done that, you can click inside the color here and just delete and start typing the name of the DMU. This is DMU1, so you can type DMU. Let me use capital letters. I have DMU1. If you were along with me, just copy, paste it here for the DMU2. So click DMU2. There you go. And then just change this to 2. But you can actually copy just the DMU, so that when you get there, you just attach the DMU to the actual name. Okay, so you just do DMU3. There you go. You go to the next one, you attach the name of the DMU, just do DMU4. Ensure that when you click it, then it changes. You make it DMU4. You will do some of these things in your thesis, okay, where you have to draw to demonstrate your methodology. This is called modeling, by the way. This is called modeling. It's called modeling, graphical modeling. Okay. So we've just done the modeling. Now you have to label the axis. And you just click on the main space here. At the top, you will see chart design at the top here. Come on. And then you click on far left, add chart element. Choose axis title. Choose primary horizontal. And then once again, choose axis title. Choose primary vertical. So you come and then rename the vertical as sales, because that was sales. Name the horizontal as staff, because that was actually staff. The data is looking very cool. Later on, you'll use the rest for something. Of course, you can always minimize the data plot the way you want. Okay, so this is what regression will do. Regression will throw a line. And in fact, you can actually throw the line right here. When you go to this quick layout here, you can now go to this one. This is layout number 1, number 9. And you can see that regression is throwing a line. So I can just click on this and throw that line right there. You can see the line. Okay. I've not accepted it yet. And when you look at the line, you can see that it also gives you the regression equation. And you can see that the regression equation is y equals to where the y is sales. So sales is equal to 0.6894 staff, and then plus the constant value that you have. So, and then of course you can check the R square. Let me put a cursor on. The R square is 73%, which means that 73% of the variability in the sales has been explained by the staff. This is a linear trend that you just pass through. Now, what the regression is doing basically is that it's throwing a line of best fit through these scatter plots. That's it. It is throwing a line of best fit through the scatter plot. Now, the interesting thing about this line is that, okay, let me accept it. I'll go back. The interesting thing about this line is that there is a deviation from this. Okay, there's a deviation between this observational point and then the actual one. Now, remember that the names have gone, okay, because I decided to. But then the plot, when you put a cursor on it, you see the data point. So if you look at it, there's a distance between each data point. So look here, this distance between each data point and the best fit line, each data point and the best fit line, each data point on the best fit line, each data point and the best fit line, each data point and the best. Some of the lines are above, some of the lines are below. These lines are known as the errors. So that when it is above, it is positive errors. Okay, that's an epsilon in a simple regression model. When it is below, it is negative errors. Okay, so these ones below, the line is negative error. At the end of the day, one of the assumptions of regression is that the mean of the error term should be 0. The expected value of the error term should be 0. So what it means is that if I should sum all these error terms and divide by the sample size of 7, okay, I should get a value of what? 0. And there's an easy way you can check it. If you run a simple regression, you can check it. How do you run a simple regression? To run a simple regression on this simple thing, you can just go to Home tab. In fact, you can rather go to Data tab at the top here. Come on. Okay. So at the Data tab on the far right, you can click on Data Analysis. And then choose regression in the list under R. Just click regression. And then you have the input Y range. The input Y range is the dependent variable, which is sales. So highlight the sales together with the title and pick all the sales. Okay. You put it there, click on the X variable, which is the independent variable. That is just staff. So click on staff together with the title and move all of them there. Okay. Now, you can take labels so that we know that we are dealing with sales. Take the new worksheet so that the answer will be in a new worksheet. And see, under the residuals here, click on the residuals. Because the residuals are the error terms. And we want to check whether the sum of them, the mean of them is 0. So under the new Excel sheet, give it a name. Call it maybe regression. I'm just calling it regression. So a new sheet is going to be created called regression. Click OK. Fantastic. A new sheet has been created. Okay. We have the R square and adjusted R square to be exactly what we had, 73%. Okay. The impact of staff on sales is exactly 0.69. Okay, that is also there. Now, of course, if you check the significant value, it tells you clearly that there's a significant impact of the dependent variable, independent on the dependent. But the interesting thing is the residual. So if of these 6 observations, were there 6 observations? Oh, yeah, yes. Okay, all right. So of these 6 observations, you check this residual. If you want to know whether they are equal to 0, just highlight each one of them. And then on the bottom, count down and come and see the average down here. The average down. If you check the average, it is 2.9659 E minus 16, which means there are 16 zeros before the 29. That simply means you have 16 zeros, which means it's basically what? 0. So that means that the expected value of the error is truly 0. So regression makes that assumption, okay? And that assumption is what is known as normality. Normality. Okay? It's one of the critical assumptions of regression. Apart from linearity, you have normality. And then the other ones like heteroscedasticity, autocorrelation, multicollinearity, indigeneity, and several others. Okay. Now, so this is what regression does. The good thing about regression is that it gives you the coefficient here. That is the impact of each independent variable on that. But then the thing is that where are the efficiency scores? I'll tell you later. Because there's an advanced version of regression known as stochastic frontier analysis. Now, what is stochastic frontier analysis is that you have the predicted sales here. Okay. And then you also have the actual sales. The actual sales is the original one that we have. And that's what created the errors in the first place. It does some kind of manipulations using different assumptions about the error term. It doesn't even assume that the error term is normally distributed. It assumes that the error term is half normal, truncated normal, censored, and several other assumptions have to be made. The specification has to be made as well, and so many things. This process is known as stochastic frontier analysis. It's an advanced version of the regression. The thing about stochastic frontier analysis, and I'm going back here, let me just go back. So regression is doing all of these manya things. Okay. Let me just select this. So regression will try, everything I've said is here. Regression will try to create a fitted line, a residual line, which I've just shown, to measure the relative efficiency. When you are above the line, so anybody that is above the line is said to be efficient. Anybody below the line is said to be, anybody above the line is said to be overperforming. Anybody below the line is said to be underperforming. And anyone on the line, take note of that, on the line is efficient. Okay. Now that is quite interesting to say that one is efficient and one is over efficient. Okay. But that is one thing the regression does. The stochastic frontier analysis, which is a higher level of regression, what it does is that instead of a regression having one error term like this, okay, you know that the usual regression is y equals to beta naught plus beta 1 x plus error term. Okay, this error term in a stochastic frontier analysis is composed. One part of the error term is the inefficiency. The other part of the error term is the noise itself. The noise is the usual stochastic noise, the idiosyncratic errors. Then the U here is the inefficiency. That is inefficiency due to managerial underperformance. Inefficiency because the managers are not doing well. It is this part of the inefficiency that the regression creates. Of course, Excel cannot calculate this. That part of the inefficiency that you manipulate and come out with an efficiency score. Because efficiency is just the reciprocal of inefficiency. So you do some manipulation with the inefficiency, the U-term, and then you can come out with an efficiency score. And the basic thing about this regression is that even though it is doing a couple of manipulations, it is still dealing with the mean. The mean is what it's still doing. It's still using the mean method. The question, however, is that when it uses the mean, what it means is that you're comparing. You see, the people above the mean, it says they are overperforming. Those below the mean, it says they are underperforming. So actually, you are being compared to an average. Question is, are you willing to be compared to an average to determine how well you are doing? Or you want to be compared to the best to determine how well? Which one? Chris, which one is the best? Isn't it? Yeah. So you compare yourself to the best, but then that is not what a regression is doing. So regression, becomes a wahala. Regression also assumes that the relationship is linear. But in life, you know that relationship can be nonlinear, can be complex, can be so many things. So again, dash. Another thing about regression is that, and especially we call it parametric regression, that it assumes generally, unless stochastic distance functions, it assumes that you need to have one dependent variable and one independent variable. So if you are dealing with cost, the dependent variable is cost. So if there are many costs, it combines them. And then there are several independent variables. If you are dealing with production, you have Y, which is a production, then several factors determining the Y. like a Cobb-Douglas production function, constant elasticity of substitution production function. Okay, you have those things there. But life is not about one independent variable. Sorry, one dependent variable. There are several dependent variables that can come. There are several factors that are determined by the independent factors. For example, if you take a bank, before you get a loan, several factors determine the loan. It's not just a deposit that creates the loans. You have workers applying their knowledge to the loans, to the deposit before it becomes loans. You have the capital involved. So you have several inputs. But the loans is not the only thing the company is producing. The company is producing investments. The loans will bring interest that generates revenue. The investment will also bring what? Interest that generates revenue. In fact, some companies will even go into real estate. The bank will go into real estate. And they can even do other income generating activities. All of these are bringing revenue, not only the loans they are giving. The loans and advances might be a greater portion, but it's not the only thing. In fact, some even do corporate social responsibility that invariably brings money. So there are multiple factors that are the dependent variables, but you can't have that in a regression because of the assumptions. Regression has a lot of restrictive assumptions. We've spoken about normality, linearity, heteroscedasticity, autocorrelation, specification errors. There's so many specifications, You got to be very precise and concise with your specification. Okay. It ignores the axiomatic properties of production theory. If you look at the basic production theory, running from consumption theory to production theory, the principle between the cost theory and all of that, you have the assumption of the cost curves, the assumption of concavity and convexity, the assumption of predisposability and monotonicity. All of these assumptions, which are fundamental to production theory, regression ignores most of them. And therefore, whilst regression is good, now this is not to say that regression is not good, it's good because it has a lot of economic interpretations that can be brought to bear. But there's a lot of complexities as well. And so that will require that we look out for another alternative. And that alternative is going all the way to the third way to assess efficiency. And that third way of assessing efficiency is data envelopment analysis, a real application of a linear programming model to assess efficiency. Instituted by Chance, Cooper, and Eduardo Rhodes. Chance and Cooper were very, very smart guys who took Eduardo as their PhD student. And then from that, they were able to come together to generate a thesis. And that was the foundation of that. Of course, these two smart gentlemen were already in the area of linear programming. Okay. So when Cooper got to know about Rhodes, and Rhodes is doing a thesis on program follow-through, okay, on some students in Texas, high school students in Texas on program follow-through, it says that this thing can be modeled using a linear programming algorithm. And so contacted Chance, who is also very good in that, and the two supervisor gentlemen, Eduardo, and eventually they came out with this beautiful model. First submitted to management science, rejected, and then submitted to European Journal of Operational Research, accepted, and sometimes it is said that management science had wished they had accepted it. So what is DEA? Unlike the regression or the stochastic frontier analysis. Now, mind you, the stochastic frontier analysis is not the only parametric method. Parametric here means you have parameter estimates. That's not the only one. We have the distribution-free analysis, the thick frontier analysis. There are several other parametric approaches that are there. But all of them are based on regression anyway. They are parametric because they require the data set to be normally distributed. The assumption of the distributional aspect of the efficiency is critical. The distribution of the noise is also critical. But here, data envelopment analysis, a linear programming algorithm approach to estimating efficiency is non-parametric, which means that it doesn't require any parametric assumptions like normality, heteroscedasticity, autocorrelation, and things like that. It is a frontier method because you're going to later see that it uses the edge, not the mean, but the edges. And as you said, it was developed by Chance, Cooper, and Rose in 1979, extended by banker Chance and Cooper when Rose has gone to do business. It uses linear programming. It purely, fundamentally, the underpinning is linear programming. And linear programming is an optimization method, but this is a frontier optimization method. It's not just it's an optimization at the frontier. The word frontier here means the boundary, the edge of something. And that is what it uses. So it is estimating the relative efficiency of homogeneous decision-making units. Why relative? Relative because these efficiencies are measured in relation to the job the others are doing. So how well you are doing in the production set is as a result of how well others are also doing. So your performance is estimated, measured, evaluated, assessed in relation to what others are also assessing, doing in the market. So you are not operating in a vacuum. You are operating in combination with operations of other people. And these firms must be homogeneous in the sense that they must use multiple inputs, similar multiple inputs to produce similar multiple outputs, several inputs. So you can see that already it solves some of the problems we have had in ratios and some of the problems we have had in regression, because they don't deal with multiple inputs and multiple outputs. Regression deals with multiple independent variables, but not multiple dependent variable. Now, DEA, the way it goes about things, in English terms, it will create a production frontier. And what do I mean by a production frontier? A usual production frontier is simply something like this. You have an X there, you have a Y there, then you create a smooth production function like this. And this kind of production function is not real. Okay? This production function is not real. Why is it not real? It's not real because things are not that smooth. In real life, things are not absolute. They are relative. But okay, this is still going to create a production function, but it's going to use a certain minimum extrapolation principle. This principle is known as two. There are two principles it will use: convexity and free disposability. Free disposability, also known as monotonicity. We'll come back to that. But why are these principles, minimal? Because it simply means that is all you need to be able to do. You don't need a lot of assumptions. Like you need to impose a lot of assumptions, on the, you need assumptions about the effort term, you need assumptions about the inefficiency term, whether his assumption is, then even the production function, you need to know whether it's CES, constant elasticity of substitution production function, whether the cost function is transcendental logarithmic function, call it translog function, whether the production function is a Douglas production function, whether it's Leontief, whether it's McFadden, and so many things. This one, you are allowing the data to talk. You put in the data. The data is made up of the entire technology. You call it and it will give you what it is happening there without imposing a lot of structures on the production technology. So you need those minimum assumption of convexity and monotonicity. I'll explain them in total, so just hold on. Now, you can do a production function, but you can also do a cost function, and you can also do a profit function. It doesn't matter which function. Okay, so that's what DEA does. That's what the data envelopment analysis is doing. But what exactly is it doing? How does it do it? Well, it will create this function from the observed data point. So if you go back to our Excel that we are about to create the function from the data set right now, okay? Keep that in mind. So this is the data set. So now I can go back here and show you everything. The regression, it's kind of, we are saying bye-bye to regression. Okay. Oh, but it appears that I didn't want to. I didn't want to remove this. I wanted to just undo. But it appears that I no longer can undo. Okay, so we got to just go back. Anyway, so if these things were like that, let me just delete it. If this thing was like this, okay, let me just use no one. I had another one. So there's another one here. You can now, this is what we plotted, if you can remember. So yeah, we made it bigger. I just want to make it bigger before we start. Data labels. Okay. I just want to make it bigger. Okay, so then I need to click on this and show the markers. So in this markers here, I can now, okay, let me just keep this one here and just increase the size a little bit. And at this stage, you can now create, so use two principles. We are going to use two principles right now to create a frontier, which is what the linear programming envelopment analytics. God, that's the name we are giving it, linear programming envelopment.
Yes, please.
Analytics. But that is the name for it. So we give this one, and then we insert some graph, some lines. Remember, we are going to use the principle of convexity. I will deeply talk about convexity, but I just want you to know something here. And that goes to you, Chris and Obed. Obed, how do you create a straight line? What do you need to create a straight line? What are the things you need to create a straight line? Chris?
You need a point to create a straight line. You said?
How many points?
Oh, 2 points can do.
Yes. So let's take that we have 2 points here, and then we have another one here. What do I do to create a line? Is by joining them, right?
Yes, please.
So like linear programming, everything on this line is possible because these two are possible, isn't it? If this is a real data set you have collected, and this is also a real data set you've collected, because they are real, then anything between these two are also possible. Do you agree with that?
Yes,
agree with that?
Yes.
Therefore, we can join these two lines. That joining of these two lines is based on the assumption of convexity. That's what linear programming does. So when you get to the constraint, if you can remember, in linear programming constraint, when you used to have something like, what do you call it? 40x1 plus 50x2, okay, for Farmagon Limited or something. And then you have constraint like 3x1 plus 4x2, okay, less than or equal to 40 gallons of, 40 hours of labor. So this is a constraint. And this constraint, you can use the idea of a straight line to get this line, isn't it? So if you assume that x2 is 0, you can find x1. And if you assume that x1 is 0, you can find x2, and you can draw a line. That line is not for the less than, it's dealing with the equal to. So if I draw the line and then the line is this, then it means that everything below the line is representing what? The less than part. Okay. So everything below the line is the less than part. And then the line itself is the equal to part. Okay. Therefore, these lines that I'm drawing are based, these lines are convexity. So it's the same principle here. So on this principle, a straight line can be drawn provided you know that 2 points are there. Now, as you can see, 2 points are here. You have DME1 and DME2. These are points, so I can join them by the principle of convexity. I'm only showing you the graphical, but you can also do the mathematical next to it. So I can take this one here. Okay, but let me use an actual one. I can take this line. So when you go to insert, okay, if I want to go to insert here and go to shapes, okay, you can pick a line and then join this line to this. You can make the line bigger through formatting, so you don't need to worry much. Okay, so let me just, okay, so make this one bigger. That is one piece wise line. Then you can copy this, paste it. Okay, I just decided to do it like that. So that I pick them one by one. So I pick another line. Oh, what happened? Sorry. Okay, let's, oh, come on. Let me just do it again. Okay, good. So you pick this second line from this point here and join it to this one there. Okay. And then you can pick the next line, okay, join it from here, and then move it to this point there. And then I pick the next one line. You can join this one from here, and then you could actually put it there. But you're later going to see why that is not useful. Okay. And then you pick this one, join it from here, and actually also combine it here. You're actually going to see why that is not going to be useful in this context. And then you can join the other one there. Now, these bottom ones are not useful. Why? The reason is because of another assumption, which is predisposability. You see, what did we say about efficiency? We said that efficiency, you draw this in an exam too. We said efficiency is your ability to cut down the input. Okay, cut down the input. So if this input is here, okay, or this point is here, if I want to cut down the input, I move leftward. It means that there is another point at this junction here that is currently has reduced its input to that point than the DMU3. If I want to increase the output, I'll go upward. Okay, there is a point here, of course, as you don't know yet, okay, because everything above the line is not possible. It's unattainable set. There is a point there that has raised the output up to that boundary than what the DMU3 can do. And therefore, every point to the right of the XY graph, okay, because this is XY graph, you can draw 3 different graphs, but this is just one. Every point to the right of the S1 graph, like all the points here, are not useful because there is another point on the line that is doing better in terms of the input or better in terms of the output than any of the points in the production possibility set here. You understand, Chris?
Yes, sir.
What do you understand? Tell me. Tell me what you understand.
Any distance from DMU3 should be the perpendicular distance from that point to the frontier. So your graph, that's what you seem to be explaining. So I've gotten it.
Okay, so let me ask you. So which point wouldn't need you to pass a line through them?
1, 2, 4, and 6.
No, I mean, which point will not require you to join a line to them? That's what I mean. To create a frontier.
will not require.
Yes. I had a point between 1 and 2. I joined a line between 1 and 2. That is possible. That is good to do. I join another line between 2 and 4. Okay. I join another line from 1 to 3. I join another line from 3 to 5. I join another line from 5 to 6. I could have done that. Which of these is not to be done? Because remember, the line is showing those that are doing better on the line. Those that are either producing the less of the input and the more of the output. And anywhere where the line is not producing the less of the input, or there is
three and 5.
Why?
Because they are suboptimal to the 1, 2, 4, 6.
That's the point.
So if you want a frontier, you should just take the highest instead of drawing it to the smallest.
Exactly. So what it means is that you don't need this line, because this very line will not be useful because these points are dominated. That's the way you say. The points 3 and 5 are dominated. And therefore, they are interior to the boundary. You see, the points on the frontier are on the boundary. Remember, this is a relative measure. So before you can actually estimate the efficiency scores and make a decision, you need to identify the points that are on the line. And actually, the points that are on the line are the points that created the line in the first place by joining them using the convexity assumption. Okay. One assumption then that you need, which is the last assumption, is not the convexity assumption, but it's called the free disposability assumption. So you close it. You see, this thing, as you can see right now, is not closed. How do you close a line? Bring the line here to close it to the origin. So that you know that this line, or this curve, concave or convex curve, is closed. You do the same thing for the next one. Okay, you go horizontal to close it. Okay, so come here, you move this thing up there, and then you close it beautifully. So now we have closed it. This closing is called free disposability. We'll explain it, but just remember that they are the horizontal and the vertical lines of the frontier. Everything inside is known as the production technology. In fact, the production technology is made up of the boundary of the set plus the set itself, the space. So the space plus the edge of the space make up what is known as the technology set. The technology. If you are taking notes, you would have taken a lot of notes by now. Okay. And that is how you. So the first thing the linear programming envelopment analytics does is that you first create this frontier using the data set. As you can see, we created a point using the data. Now we join these points using the convexity assumption. And then we now have estimated our frontier. So what's the next thing? Let's go to the note after you've created a frontier. Because it says that you create the frontier based on the unit you have observed using the best practice DMUs. That word, best practice DMUs, are those DMUs that are on the far northeastern part in the SY graph now. North, south, east, and west. So northwestern part of the graph, they are the ones that you actually identify. And when you look at these ones here, you see that this 1, 2, 4, 6, they are on the northwestern part of this graph. Okay. And there's no other unit that is on their left or on their top that will dominate them. But when you look at unit 3, there is a unit on top of it or on the left of it that is dominating it. The same thing with 5. Okay, so we've estimated our frontier, the boundary of the set. What next? The next thing.
Please, can I ask a question?
Yeah.
Let's go to the graph where we have the points 3 and then 5. The graph, yes.
Yeah.
If 0.3 and 5 were supposed to be above, let's assume 0.2 and then 4.
What will happen?
Yes.
Okay, so let's take a point here that 3 has gone somewhere here, and then 0.5 has gone somewhere here, something like that, right?
Yes.
When that is the case, you will have to redraw the entire frontier. The frontier will start from here, okay? It will move past 2 because 2 will be dominated. It will move straight to here, and then it will move straight to there, and then it will close at this section. Sorry, it will close at that section. Okay, so it means that at this stage, this 4, 2, and 6 will be dominated, and a new frontier is now created for all of them. So you are always taking the extreme top left section. Those that are on the extreme top left. This is only graphical. Mathematically, they are true as well. And the reason is because remember that the further up you go, the more output you are producing. And the further left you go, the more input you are reducing, which is what defines efficiency. Because as you are coming below the input section, you are moving towards 0. Of course, you will never be 0, but you are moving towards 0. But if you can use less input to produce the existing output, then you are efficient. So the whole essence is, how can I be efficient? Well, those that are on the stream relative to you have already shown that they can be efficient. And that is why the frontier will depict them as being extreme northwestern part of the book. Does that answer your question?
Yes, Doc.
Okay, so now we are ready. Once you've estimated the frontier, what next? Well, this is how you now estimate efficiency. Because remember, you've estimated a frontier. So how do you get efficiency score? Well, the efficiency is relative. That's one thing you should know. It's relative means that it is in relation to how the others are positioned. So this technical efficiency or inefficiency of a DMU is assessed by the most important term, the distance it is from the constructed frontier. So the efficiency frontier you've created, how far each of the units is from the estimated frontier would define its level of efficiency. Now that distance is a linear distance. It can also be a non-linear distance in later times. You see that. Linear here means that when I'm on the frontier, you just go to the graph. Okay, and let's say I want to be able to reach a section of the graph. If I want to reach a section of the graph, one thing I can do is I can just come here, and suppose I want to, I'm at the section here. I can move linear here. I can move linear here. I can move linear here. Everything is linear. I can move linear here, and I can move linear there. These distances, all of them have got advantages and disadvantages. Some of them are better than others. Some of them are different from others. They are all linear. But you can also do nonlinear movement, okay, where you can move, this way. I was trying to move a curved way. Okay. That's like a curve. These curves are sometimes called hyperbolic distance functions. Okay. So there are different movements that one can do. The key point is that everybody now, its distance must be measured in relation to the frontier. Now, it's interesting. What do you think the distance for the DMU to the frontier is going to be? Robert, what do you think the distance from this DMU1 to the frontier is going to be? Godo.
It's going to be linear.
Yeah, but what is the value of the distance? That's my question. How far is... Sorry?
Is it one?
No, how far is this DMU1, which is a dot here, how far is it from the frontier, red frontier? The distance. The distance. Okay, let me tell you something. What I mean is that, you see this value here is 6, right?
Yes.
And this value here is 7, right?
Yes.
Now, suppose I have something here, point A here. The thing is not moving. But suppose I have the 6, and then I have the 7, and I'm looking at the distance between 6 and 7. What is the distance?
1.
It's 1, isn't it?
Yes.
What is the distance between 8 and 6?
It's 2.
Is what?
It's 2.
It's 2 units.
Yes.
Because look at the distance. You move 1 step and another step, 2. Okay. So my next question to you is how far is the distance from this DMU1, which is a blue point, to the frontier, which is this whole frontier? How far?
It's already on the frontier, so 0.
It's 0. That's the point. Because it happens to be at the frontier. So there's no distance. It's 0.
Okay.
So the moment you have a situation where a DMU's distance to the frontier is the same, is 0, it means that the DMU is already on the frontier. And if the DMU is already on the frontier, you don't need to calculate how far is it from the frontier, because it is the frontier. And therefore, its distance will be 0. You see, the further away you are from the frontier, the more inefficient you are. The closer you are on the frontier, the more efficient you're becoming. And therefore, if you are on the frontier, you are fully efficient, or you are efficient. I think that makes sense. So we now have to estimate how far each guy is on the frontier. And it becomes obvious that those guys that are on the frontier will have an efficiency score of what?
1.
1. Because you're already on the frontier. So it will be the distance from, and the way you calculate these distances is very important. And this is what you got to memorize if you don't know, you can't understand. It's always the distance from the firm, like the distance from the origin to the frontier. Take note of this definition. The distance from the origin to the frontier divided by the distance from the origin to the firm. That's it. This is how you define how efficient a unit is. It's actually true. It's actually true when you take note of it. And we'll look at these calculations later. But just note that that is how you define efficiency. So just write it down. So efficiency, we'll use the word theta to represent efficiency. And by the way, take note that this efficiency is the same as the objective function value in a linear programming balance. It's the same as, so if you want to know what objective function value is, note it down. That is the efficiency score. That is the efficiency score. Sometimes in the literature, they use theta here to represent input efficiency score. Take note. And then they use phi, the Greek letter phi, to represent output efficiency score. So you have input efficiency score and you have output efficiency score. Either of them is defined this way. The distance from the origin, remember, it's from the origin to the firm, to the frontier, okay, from the origin to the frontier, and the distance from the origin to the firm. Now, where is the origin? If I want to do that of DMU3, the distance from the origin is here. It's horizontally from here to the, okay, let me do the first one. The distance from the origin to the firm will be here, like this. You get to the firm, you stop here. And then the distance from the origin to the frontier will be like that. Sorry, the distance from the origin to the frontier will rather be the first one. And the distance from the origin to the firm will be this. In this case, which one will be shorter? The distance from the origin to the frontier or the distance from the origin to the firm? Which is shorter?
Origin to the frontier.
Yeah. Anytime the distance from the origin to the firm or the unit is more than that of the frontier, the firm is inefficient. Take note. All right, we'll come back to that. So let me just take you back now to here. So here's the thing. So what the linear programming envelopment analytics is doing is that is identifying the frontier guys as what? As efficient. And then those that are not on the frontier as inefficient. We now understand why. It will now identify the sources of the inefficiency. What is making these guys inefficient? And this is real. What is making them inefficient? Is it their labor? Is it their capital? Is it their what? What is actually driving the inefficiency? You can dig deep. In fact, there's a method known as multi-directional efficiency that looks at the inefficiency of every single variable. Every single variable, whether it's labor, it's capital, is this, is that, is material, every single variable, what is making it efficient or inefficient? Will identify. Second, it will rank them, those that are efficient and inefficient, it will rank them. It will rank these DMUs. It will identify improvement targets. That is what it's going to do to be efficient. What specifically should you do to be efficient? It will identify targets. It will identify slacks. It will identify surpluses, input excesses, output shortfalls. And you can use it to now assess the management performance, the overall management tool. And you can use it to determine the effectiveness of programs, policies, and so forth. Very practical, very practical. Analysis will do all of this. You can graphically show them beautifully. So let's go back here and then see what we've already done actually. So what the envelopment analytics, the linear programming envelopment analytics is doing is that it is creating a frontier using the minimum extrapolation principle. That is using the convexity and the monotonicity assumption. I've said already, we'll explain this deeply. Then it creates a piecewise linear frontier envelopment. So it does the piecewise linear frontier envelopment. That's what it's doing. It will close it at the bottom and then it will close it at the top here so that it becomes closed. Once it's done that, it will now do something interesting. You see, it will construct the piecewise linear convex envelopment. I've said that from the data. That is what it does to create a frontier. It will identify a portion of those best practice guides that are now used to construct the efficient boundary, which is what we've done here. So these guys were used to now construct the green efficient boundary. We call it the boundary of the production possibility set. And this boundary will envelope every other. But those guys that created the frontier, they will be on the frontier, not in the frontier, or not in the production set, but on the boundary of the production set. That's why they are efficient. Now, the efficiency of everybody, something I've said already, is now assessed relative to the boundary that has been created, either using the input direction or the output orientation. So you can see this is the production frontier. Now, this whole thing is a technology set. That is both the space and then the line at the edge. A DMU on the frontier is efficient. DMU below the frontier is inefficient because that DMU has been dominated. There is some portion of the frontier that covers it, that envelopes it, that dominates it. Now, if you look at it, because staff has to be reduced and sales has to be increased, the dominating guy, that is the superpower guys, are on the northwest of the dominated point. I said this before. So somebody said, how do you get to know those that are efficient? You get to know that are efficient because they are on the northwestern part of the graph, graphically speaking. When we come to the mathematically speaking, you will see how they actually look like. They are usually on the left side of the production, what do you call it, of the technology set. The left-hand side of the constraints, the left-hand side of the constraint, they define the frontier. They define the boundary for the frontier. And actually, their definition is in the equality symbol, not in the inequality symbol. So actually, if you really look at the linear programming, everything on the line will be the equal part of the constraint. Because actually, if you look at these lines are the constraint lines. So normally the constraint lines are like this. You draw the lines like this, if you can remember. Then you draw the lines like this, you can remember. Then you draw the lines like these, you can remember. And then these lines, they meet. And when they meet, we call it the vertex. Did you guys learn that in linear program? The vertices. Yeah. So once you get the vertices, we call it the corner points, the vertices or the corner points. They now make up what? The point you are interested in. Then you try and see which one is not conflicting with the rules. And then this particular corner point, these vertices, you try and find the coordinates. Once you find the coordinates of these corner points, then you check whether when you substitute these coordinates back into the objective function, they maximize the positive outcome or they minimize the negative outcome. And that's how you identify your optimal solution points. Well, trust me, here, we already know these optimal solution points because there are quite many of them for the unit. And so these corner points, they make up the vertices. And they have already defined the frontier that you're looking for. All right. Now, input orientation. We have an efficiency score, input-oriented efficiency score. What is that? It's simple. A DMU is you know, the input-oriented efficiency of a company is the percentage to which all the inputs are reduced without reducing the output. That's all. In other words, input-oriented efficiency score is when the firm holds all the output constant and still reduce the input and still produce the same output. Can you imagine that? You have 10 workers, you reduce the 10 workers in a year, you reduce the 10 workers to 4. The 10 workers were producing 50 bags. And when you reduce them to 4, they are still producing 50 bags. That means you're efficient as a manager. That's it. That's input efficiency. You are reducing the input. And how do you do that in the graph? Well, in the graph, when you check it, input efficiency will require that you move leftward, like that. That's what it means. Input efficiency requires that you move leftward. So if you are here, you move leftward. If you are here, you are moving leftward. If you are here, you are moving leftward until you hit the frontier. Move leftward until you hit the frontier. Move leftward. So as you are moving leftward, you are cutting down the star, which is the goal of being efficient. That is why in some markets, managers don't care to cut down workers because the workers are costing them a lot of money. So if there's too much, that's why you also notice that most government institutions don't pay much because there's so many workers. And so they are paying so much salary that the salary are not that many. But most private institutions, they'll fire you. It's called fire and hire. So many people tend to behave well when you're in private organizations than public ones. Because staff or the input, either the number of staff or the staff cost. So sometimes they know that if they fire you, they are not going to get a lot of public good image. And so to prove that they are very good, they will rather cut down your salary and keep you. But sometimes some of the salaries are in such a way that if they are fired, you is even better. Oh my God. If they are fired you. I spoke to somebody who's worked for 27 years, and then his income has gone up by so tiny. The income, first of all, wasn't that many, and it's not gone up even by 40%.
Mm.
That tells you. But it's going up, actually. It's going up, but just that it's not gone up. The thing is going up, but the way it's going up, it's like you're 99-year-old madam who is walking. The thing is going up, but it's going up 0.004, 0.000004. Like that. It will keep going up like that. By the time you realize you're 60. Now, if you are on the frontier, you're efficient. If you are below the frontier, you are inefficient. Okay, we know this already. So which DMUs are efficient and which are inefficient? Oh, but are you here? Which DMUs are efficient and which are inefficient?
The inefficients are DMU 3 and 5.
Good. Because they are dominated. Okay. Now, so what it means is that we need to now calculate the inefficient, because what you said was graphical. Okay. Now, what should DMU5 do to become efficient? What do you think DMU5 should do? Let's look at it here. If you look at DMU5, to become efficient, what should they do? Obed, still you.
It should move leftwards.
It should move leftward.
Yes.
From where to where? From which point?
From the point of 6.
To the point of?
To the point of?
Approximately?
Approximately 3.
Good. So in this case, which efficiency approach are you using? Input efficiency or output efficiency?
I'm using inputs.
What if it is the output? How should it move? Rado, what would you say? If it is output?
Okay, so if it is output, then we're going to hold the input constant. So you move upwards.
Okay, you move upwards. So it's going to move upwards from what to what?
So you should be looking at producing output from 4 to somewhere around 3.5.
Let me the from first.
So currently the output is 4.
Good. So you match it here. That's the point I want us to see. So the output is 4. Match it here. And you should increase it to what?
Around 5.5. So.
Around 4.5 thereabout. Exactly. 5.5. So that's how you do the measurement, guys. Chris, are you following? That is how you do the measurement. Okay. So you should know how to do. So the first one, reduce the staff. That's input direction. Move the horizontal distance. And then you do to get to the point. And when it does that, it's going to get something like 3.5, which is and we look at the distance here. You see, the first one, it says you should move the DMU5. So if you check DMU5, let's go and check DMU5. So DMU5, look at where it is. Where is that? Is it DMU5? Okay, yeah. So how do you, in the input direction, so this is in the input direction, the DMU5 will have to reduce the input from 6 to 3.5 thereabout. Okay. So if you want to calculate its efficiency, remember we said that you always start from the origin, because in the input direction, the origin is down here, but if you move upwards horizontally, it also is the same as up here. So the origin is 0 at this point. Okay, when you come match it down. So the distance is going to be distance from the origin to the frontier. The one I said you should memorize. That's how you always calculate efficiency, which is that 3.5. Okay, so is this 3.5? Then the distance from the origin to the fan, which is 6. Okay, so if you want to know the efficiency of DMU5, it is the distance from, so it's efficiency of input. So that is input efficiency for DMU5. And this is going to be the distance from the origin to the unit. Okay, sorry, from the origin to the frontier. Always Remember, from the origin to the frontier, divided by the distance from the origin to the unit or the DMU. And the distance from the origin to the frontier is 3.5. The distance from the origin to the unit is 6. Therefore, 3.5 divided by 6 is 0.58. So you now know that the current efficiency level, the current input efficiency level for the DMU5 is 3.5. No wonder its score.
I have a question. Yes.
Yes.
Doc, should it be the distance to the origin, or it should be the vertical or horizontal distance to the Y or X axis?
Well, so in this context, because you are looking at
Because technically the origin is 0, 0.
Yeah, the origin is 0, 0. So in this context, you look at the horizontal distance from the origin to the frontier divided by, and you can match it here because what I read was matched down here. So if you want to be specific, that's how it is. The horizontal distance from the origin to the frontier. But when you get here, you read it downward. And then the horizontal distance again from the origin to the fan, which you have to also read it downward. If it is vertical, okay, the same thing. You will say that the vertical distance, so in this case, you go like that. The vertical distance from the origin here to the frontier there. We'll come back to that. That's our output orientation. Okay, that gives you this. Okay. So that would be something like, we match it up here. It is 5.5 thereabout. Then you say the vertical distance from the origin to the fan, which in this case is 4. When you match it to the left, it's going to be 4. So you now have 5.5 divided by 4. Now, 5.5 divided by 4 will give you a value that is what? More than 1. So one of the rules you're going to learn later on is that the output efficiency score is 1 or more. Write it down. And the input efficiency score is 1 or less. So for the output efficiency score, if the DMUs are 1, they are output efficient. And if they are greater than 1, they are output inefficient. But for the input, if the DMU are 1, they are efficient. And if they are less than 1, they are inefficient. Chris, do you follow?
Yes, Doc.
Let's proceed. So that's how you do the efficiency for that. And you can do that. So we've done it for DMU5. You can do the same thing for DMU3. And on the basis of that, these are given here. And you can do the same thing for every other DMU. But just note that the output efficiency scores are 1 or more. Where 1 is efficient, more than 1 is inefficient. The input efficiency scores are 1 or less. 1 is efficient, and below 1 is inefficient. Keep that in mind. It's very, very important. Okay. All right. Now, everything we did was in an XY graph, but also it was in input-output graph, if you could remember. It was input-output graph because on the x-axis is input, on the y-axis is output. But sometimes the graphs are in such a way that you can normalize the input or you can normalize the output. Let's look at a situation where you normalize the output. Now, what do I mean by normalize the output? In other words, you can assume that all the DMUs are producing the same output. All of them are producing the same output. Okay, so what do you do? Well, if they are all producing the same output, you can ignore the output because it's normalized, it's 1. Okay, because we are all doing the same thing. So let's leave that part. Where we are not doing the same thing, now we are going to compare. That's where the relative comes in. So we're going to assume that this time the inputs are 2 and the output is 1, but the output is normalized. The same output, but then the inputs are different. So we are dealing with stuff and materials. How do you draw it? Well, so in this case, you're still going to have XY graph, all right, but you're going to have input X2 rather here and input X1 rather there. This reminds you of something called isoquant. Isoquant. And then when you are dealing with the production, we call it isoquant. And when you are dealing with the cost, we call it isocost. So we can say that let staff be this one here, and then let materials be the one on the axis there. How do you now determine efficiency? Well, it's the same approach. Use the definition in your head, but then the way you do the movement is different. So follow. In such a case, then efficiency, still using that, okay, is no longer going to be horizontal or vertical distance like we did. Okay, it's no longer going to be that. It has to do with the, let's define it. It's going to be the distance from the origin, again, to the frontier, divided by the distance from the origin to the unit. Never forget this definition. It's memorizable. Okay. But in this case, we can't move horizontally or vertically, because now it becomes clear that if we are far away and coming towards the origin, we are rather reducing input. For example, if you're on the X1 and you go leftward, you're reducing the input. If you're on the X2 and you go rather downward, you're also reducing input. So the input reduction are all moving towards the origin. So in this case, both ways, you can now move on the origin rather towards, you can all rather move from the out of the origin towards the in of the origin. That's what we mean by the movement now. So how do you use that to determine efficiency? This is it. Let me give you an example. So efficiency is not determined. So when you have you plot these ones for each input and output, if you plot all of this, then efficiency of a unit will be defined as the movement. So let's say a unit is here. Okay. Then it will be the distance from this unit, from the distance from the origin to the frontier, divided by the distance from the origin to the unit. The same thing. If the unit is on this section here, is a distance from the origin to the frontier divided by the distance from the origin to the unit. That's how it is. That's how the efficiency is. So this movement towards the origin is very important. Why? Because as you are moving towards the origin, you are maintaining the ratio of the input and of the output. You are maintaining the ratio. The origin keeps the ratio intact. So along that line, along the movement along the line towards the origin, the ratio between the X1 and the X2 is maintained. And that measure is what led to the idea of radial measure. Radial. Yesterday we spoke about it, proportional. It's the same as a proportional measure. So you are maintaining the proportion of this. So if I give you a data set and I tell you to plot these frames, and you plot these frames, you should be able to identify the efficiency of every frame. Now, once again, all the frames that are on the frontier will be efficient because their distance from the origin to the frame, to the frontier will be, oh, by the way, you read it down here. And in this case, because the ratio is the same, you can read it down here or you can read it left there. But whichever one you are reading, keep that. Don't mix them. So the distance from the origin to the frontier will be here too. And suppose I want to rather do another one and the other one is here. And that distance from the origin to this frame will be 3.5 here. So it means that for this very example, it's going to be 2 over 3.5. And then you can calculate that score, that input efficiency score. But what if the frame is on the frontier, like this one here? Again, the distance from the origin to the frontier is going to be 5. You read it down here. And the distance from the origin to the unit is also going to be 5. So you're going to have 5 divided by 5, giving you 1. That's why the firms on the frontier are said to have an efficiency score of 1, which means that they are fully efficient. Any question? So that is how you do the estimation. Now, what if it's output? Well, what if they are output? Output efficiency, I said we use the word 5, the Greek letter 5. Okay, so 5. Okay. Now, I also said that output efficiency, more than 1 is inefficient and equal to 1 is efficient. But sometimes it confuses. So you can easily take the reciprocal of the answer and it will bring you back to the between 0 and 1. And it's the same thing. The interpretation of whether it is efficient or is not efficient is the same thing. But there is another interpretation that will not be the same. We'll look at that later. So let's take an example. Okay. If you take this one here, okay, we've already said that the output efficiency is when you're going up. This is in the X and Y graph. No, not X, Y1, Y2. But this is in the X and Y graph. Okay. And we have already done this. So you said that the distance here, you read it on the left, okay, and bring it down, and then you read it on the other side. However, one thing is that I didn't draw the output efficiency, but let me show you what the output efficiency might look like. Suppose I was to do the output efficiency, it would be something like this. Y1 and then Y2. But remember the input efficiency was something like this. Okay? The output efficiency is the opposite. It could be something like that, this, then that. This is the output efficiency. Okay. Where the unit, so you might have the unit to be maybe this one here, this one here, this one here. Okay, let's put it here. This one here, then you have this one here, and then you have another one, another one. So you can have this kind of, and then you can estimate the distances. So again, you start from the origin. If I want to know whether this guy is efficient, oh, that's simple. All you got to do is to take that distance from the origin to the frontier, but he must pass through the firm. Okay, then you record the value. Where do you record the value? You record the value down here. And then you now take distance from the origin to the firm, okay, where the firm is. Then you record the value. The value is down here. So you can now look at these two values and you can say, oh, maybe this one is what? 2. And maybe this one is what? 6. So on the basis of that, the distance to the frontier is 6. Now remember, we are using 5. So you write 5 for that particular DME. Okay, let's say that this DME is DME A. So you say 5 to the power A. And the distance from the origin to the frontier is 6. Divided by the distance from the origin to the unit is 2. Okay. And therefore, you can now take your calculator and find the value of the 2. So you take a calculator, you take 6 divided by 2, and that gives you 3. Now this value is above 1 in output-oriented efficiency terms. So is the firm efficient or inefficient? Yes. Is the firm efficient or inefficient?
A score of 3.
Yes, output-oriented score of 3.
I think it's not efficient.
Sorry?
It's not.
I'm here.
Why do you say it's not? Explain. Obed, why do you think it's not? Why is this firm not efficient?
I think the rate of substitution is not equal. It's not equiproportional.
What does that mean? Well, we said that for output-oriented efficiency, take note, the output, in case you don't know, write it down. The value of the efficiency is between is between 1 and above. So the theta must be greater than 1. That is it. Output-oriented efficiency, write it down. And when it is equal to 1, we say the firm is what? Efficient. But when it is greater than 1, the firm is inefficient. That's what we said. And this is output-oriented score. So now that this score is what? Is equal to 3, is it efficient or inefficient?
It's inefficient.
Inefficient. But how do you know? Well, you can see that this was a guy. The guy is here. The guy was supposed to move its output to the frontier. And look at the distance it is away from the frontier. The guy is suffering. So there's a gap between where he is now and where he should be. The key point now is to raise these two outputs. One of them is here, okay, 2. Another one is here, 2. He has to move them all the way to 6 here, and 6, representing 6 here and 6 there, before it can be efficient. So right now, as it stands, he is not efficient. And that is why his efficiency score is what? It's 3. But you can take the reciprocal of this value so that it becomes easier to understand it in an oriented sense, an input-oriented sense, because we said that for most efficiency, it makes it mentally clear that when it is between 0 and 1, and we know that when is 1 is efficient, when is below 1 is inefficient. So take the reciprocal of this. It's just to help you to mentally understand what is going on. And when you take the reciprocal of this, it's going to be 1 divided by 3, okay, which is about 33%. And therefore, you can now say, oh, okay, so this firm is 33% efficient, which means it's not 100% efficient, which means it's inefficient. So understand the output-oriented measure is very important. Okay. And ask questions when you don't understand them. So that is how you estimate an output-oriented. Now, you should know that we can estimate something that becomes here, once it's on the frontier, is efficient. So if you take this unit here, this unit is efficient because it's on the frontier. This unit here is efficient because it's on the frontier. This unit here is efficient, okay, because it's on the frontier, but there's a question mark. And we'll look at this question mark next time, because it's not all the units that are on the frontier that are efficient. Mathematically, it is not so. I mean, you can see, if you have a mathematical eye, you can quickly see that. See this guy here. Look at this guy here. See, this guy here is, we say this guy is on the frontier, but he's efficient. But this guy too is on the frontier, but he's efficient. But there's a problem. There's a problem with this guy who is on the frontier and claims to be efficient. There is a problem with this guy here. Let's call this B. There's a problem with B. Why? Because if you carefully look at B compared to C, they are all using, let's say, output 8. They're all producing Y1 at 8. But when you match it to the output Y2, B is producing, say, 1.5. And when you match C to output 2, where it is, it's producing, say, 4. So technically speaking, if you look at C and B, who is more efficient? Chris, who is more efficient?
C.
Why?
Well, because the output combination is more than that of B.
Exactly. Exactly the point. Exactly the point. Exactly. So even though they are all on the frontier, it doesn't mean that they are all efficient. But then the Farrell efficiency score, the one we looked at yesterday, will say that B is efficient. But then the Pareto-Koopman's efficiency score will tell you that B is not fully efficient. In fact, B is usually said to be weakly efficient. You look detail into that. Okay, so even among the super guys, by the way, that's why you will use a slack-based measure.
Right.
Because a slack-based measure will penalize B for being inefficient on slacks, because here B is generating slacks, which is this level. And these slacks will have to be incorporated into its efficiency score, and it will drop its efficiency score down. And therefore, when you use the simple, linear programming envelopment analytics model, it will simply say B is efficient. But when we use the slacks-based model, it will tell you that no, he's not efficient because he's generating some mixed inefficiencies also.
Okay.
So that is an important thing. But I want you guys to know the difference between the input-oriented efficiency score, how is it calculated, as well as the output-oriented efficiency score, how it's calculated. Okay. So in real-life situation, the production function that we know in economics, okay, the production function is not known. You can't see it in reality. That's why in economics, absolute efficiency doesn't work. That's why relative efficiency is important. That is why we talk about relative, because we gather data and you're able to mimic the population based on the observed sample you've taken. Most of the efficiency comparative analysis are focused on the measurement of relative efficiency, not absolute efficiency. So take note, we estimate efficiency after collecting data. So if you don't have data sets, you can't do efficiency analysis and you can't make decision analysis. The decision that will come from this is either you increase the input, you reduce the input, or increase the output. Okay. The decision that will come is making improvement targets. The decision that will come is what can I do to cut which variable down? What can I do to raise each variable up? Those are the managerial decision analysis. So do this between the two of you and submit this assignment to me. You will have just 3 assignments in this part. Very, very short assignment. So we've done this already, but I want the two of you to do it and submit it to me. Number 1, take a company, any organization in the public sector. Identify the DMUs in that public sector. Okay. In that public sector, take one organization and then one in the private sector as well. Identify a set of DMUs that belong to each, the public and the private. Okay. Just do 5-5. Then just pick one of the, the DMUs, one. And in that one, tell me the inputs and the outputs. Okay. Tell me the input of the output that will make up that DMU. Again, they should be 5-5. Comment on any shortcomings reflecting fully the input and output. That's what you should do. The second one is you have this data set.
So I have a question. So the first one, do we get any data?
No, you don't need the data. You just need to think.
Okay. All right. Okay. So theoretical. All right.
Yeah. The second one here, I've given you a hypothetical data set of outputs as well as 2 inputs. Now, what you have to do is consider the following data 5 things. You have 2 inputs, capital and labor. They produce a single output. Okay. Now, you are not going to let the data speak using efficiency analysis, using the linear programming envelopment analytics I've given you. What you are going to do is, I've given you a production function. And yours is to calculate the absolute output efficiency score for each firm. It's simple. Given this function, you know what X1 is, you know what X2 is. You're going to now substitute that here. But first, you need to calculate absolute efficiency here. And then you now calculate you substitute the X1 and the X2 here. Now, indicate how you will interpret the scores. Indicate clearly how you will interpret the scores. Okay. Illustrate the problem graphically, because you have the data, you have the function. Plot the two inputs against each other. Tell which DMUs are more efficient. Plot x1 over y. So when you take the x's, you have x1 over y, and then you have x2 over y, like that. What does this transformation, when you do it that way, what does that achieve? What assumption is implicitly made when considering these two ratios? Okay. When considering the ratios instead of considering them individually, okay, is assumption met? Can you tell the level of efficiency of the DMUs from the figure? Okay. How do you relate to the previously calculated scores, the one you didn't do the division? Do that as a group and then submit that for me next time. Gentlemen, this brings us to the end of the entire caboodle. Any question? Any question? Fantastic. So next time we are going to learn how to estimate this. See, you've learned the graphical means. Next time you're going to learn the linear programming connection with this. You're going to connect this to linear programming, and you see the beauty of it. Now remember, this is practical that you are already. So what this means is that if you have a particular company in mind or industry in mind, once we get the data, and most of the time it's good to take industries where their data is publicly available, like banks, like insurance companies, those that are easily obtainable, like countries, electricity distribution companies, things like that, unlike churches near here. Once you get that, you already have a thesis, and you already have something. We'll look at how to model, bring the linear programming slowly, how to do that mathematically. And then we shall use our software to practically estimate efficiency scores. Guys, the results you had before, we shall use R to do that so that you can see how we got it. Fantastic. So that's it for today. Enjoy the rest of your day, and we'll meet again next